In this video, we're going to talk about substitution. So we're going to start off with a quick definition. So the indefinite integral is not anything new. It's simply the collection of all antiderivatives for a given function. We denote it as an integral of our function little f of x without any bounds of integration. So we already know several of these. We have a small table down below. So we know the antiderivative, or the indefinite integral, for monomials, as long as the power is not -1, cosine, sine, secant squared, secant x tangent x, cosecant squared x, and cosecant x cotangent x. So our goal is to extend this list using a rule that we can think of as sort of reversing the chain rule. So we're going to start off with the actual chain rule. So the fundamental theorem, part 1, tells us that if we integrate both sides of this thing, we'll get an antiderivative. This is unsurprising because we started off by differentiating a function and then claiming that the function that we differentiated is an antiderivative for its derivative. That's obvious. However, our goal is to be able to identify integrands that came from an application of the chain rule. To make this formula easier, we introduce a new variable, which we call u. We compute the derivative of u with respect to x, which is just g prime. And we write a new expression, du is equal to g prime of x dx. This allows us to rewrite our integral as, so while the addition of the u doesn't actually change anything, it helps us to identify how the integrand came from an application of the chain rule. So let's do a couple of examples to see how this works. So our goal, whenever we're doing u substitution, is to pick u in such a way that we end up with one of the functions for which we know the antiderivative. In this case, that function is going to be cosine. So we're going to choose u to be x to the 4th plus 2. We're going to compute du by taking the derivative of x to the 4th plus 2. Now we're going to look at the pieces that we have. So we know how to replace the x to the 4th plus 2. So the remaining x's are the x cubed and the dx. We have an expression involving u, which is du equals 4x cubed dx. But we only have x cubed dx in our integrand. So we can move constants across the equation. However, we cannot move variables. So we can divide both sides by 4 to get. So we can see that we can replace the highlighted pieces of our integrand by 1 over 4 du. So we see that our antiderivative is 1 over 4 sine of x to the 4th plus 2, and all antiderivatives of x cubed cosine x to the 4th plus 2 are obtained by adding a constant to this function, which is why we've put in this plus c to stand for the whole family of these antiderivatives. Once we have an answer like this, we can always check it by differentiating and seeing if we get our integrand back. Since the derivative of 1 over 4 sine of x to the 4th plus 2 is x cubed cosine x to the 4th plus 2, we know that we have the correct answer. For this one, the integral that we should expect to do should be something like u to the minus 1/2 power. That means that we want to choose u to be 1 minus 4x squared. If we compute du, we'll get minus 8x dx, and we can solve for x dx. Once we have this expression, we know how to replace the x dx, which is highlighted here in blue. So we can replace 1 minus 4x squared by u, and we can replace the highlighted piece by negative 1/8 du. And again, we can check that our answer is correct simply by taking the derivative. In our next example, the substitution is slightly less straightforward. So for this one, we might like to think about this as being something along the lines of integrating the square root of u. In that case, we would have to choose u to be 1 plus x squared. So du becomes 2x dx, and x dx is the same thing as 1/2 du. However, if you notice over here, this highlighted section has more x's than our expression for du. Namely, we have 1/2 du is equal to x dx, but we need to replace x to the 5th dx. In this case, we can be a little bit clever. We can take our substitution and we can solve for x squared. So we can think about x to the 5th dx as x to the 4th times x dx. So if we square this expression for x squared, we'll get an expression for x to the 4th. By doing this, we now have a way to replace the square root of 1 plus x squared, x to the 4th, and x dx. That gets rid of all three pieces. While this new expression might not look any better than the one we started with, we can make the observation that now the place where we have, in this case, subtraction instead of addition, the power is an integer power, which means that we can expand and we can express this square root of u as u to the 1/2. Once we've expanded, we can distribute that power to each of the terms and compute this thing sort of like a polynomial. Each of these have been indefinite integrals. If we want to compute definite integrals, then there's a nice formula for how to change the bounds. So this says when we make the substitution, u equals g of x, we plug a into the function g. That becomes our new lower bound of integration. We plug b into g. That becomes our new upper bound of integration. And we carry it out the exact same way that we have in the past. So let's do an example. When I look at this, I think that it should basically look like the integral of the square root of u. So I'm going to take u to be 2x plus 1. I'm going to compute du. This little computation tells me how to replace the 2x plus 1 inside the square root as well as the dx. I'm now going to plug 0 in for x in the expression u equals 2x plus 1 and also 4 to get my new bounds of integration. So when we make the substitution, we also change the bounds of integration. There are two other nice consequences of this new substitution formula. They have to do with symmetry of a function. So we're going to assume that we have a function f that is continuous from minus a to a. If f is an even function, then we know that our function has symmetry about the y-axis. If f has symmetry about the y-axis, and I wanted to integrate from minus a to a, then it should be clear that the area of the region from minus a to 0 and the area of the region from 0 to a should be the same size. This formula simply expresses that geometric observation. So this formula just tells us that because our function has symmetry about the y-axis, this region on the left and this region on the right should have the exact same area. So this says if you want to measure the area of both regions, it's enough to measure the area of one region, that's the integral from 0 to a of f, and then simply multiply it by 2. For odd functions, something similar happens, except that we remember that our odd functions have symmetry about the origin. So whatever is seen in the first quadrant gets reflected into the third quadrant, and whatever's in the second quadrant is reflected into the fourth quadrant. So if we integrate from minus a to a, instead of getting twice a value, we actually get 0. So whatever we see up here in the first quadrant, that's above the x-axis. This piece in blue here, by symmetry, is the same size as this piece in red, which is below the x-axis. So if we measure the area here and we measure the area here, they are the same area. However, if we remember that the integral signs area according to where it is with respect to the x-axis, the blue region is positive. That's the integral from 0 to a of f, while the red region is the integral from minus a to 0. That picks up a negative sign. Since they are the same in magnitude, but the opposite in sign, when you add them together, you'll get 0. And that's it.